Hello, Chemistry 12. This is Mr. Chan here. And today, what I wanted to do was talk about the second part of solubility equilibrium. And we're going to be focusing on the grade 12 portion of solubility. Now, back in the previous videos, what we had talked about was we had talked about identifying low soluble compounds. And back in grade 11, remember on your solubility table, what you would do is, this was in our video last time, we would determine whether something was soluble or stays a solid in solution. So we said it was soluble or low solubility. In actuality, that is not the case. So if I were to do my whoopsie, here we go. Now, what happens is all low soluble compounds, they actually do dissolve to some degree. So here, in this particular case, all low soluble compounds or insoluble compounds do dissolve to some degree. Okay. And when they do, they tend to form saturated solutions readily to establish an equilibrium system. Now, let me see if I can get this down here. Now, the one thing that you need to be aware of is this. Here, let me see if I move this over to the side. Okay. The term saturated solution and equilibrium system, these are the exact same thing. Equilibrium and saturated solutions, these are the same. Okay. And we had talked about this earlier in our in your notes from before when we did the solubility introduction. Okay. And in your notes, remember it was, if we had scrolled down a little bit here, remember we had it, I even highlighted the word saturated solution is the same as equilibrium. Okay, so just something for you to remind you. Okay, now, so if we take a look at this, so let's say we consider AgCl. Now, if we took a look at AgCl, what happens is AgCl, this was not soluble. When we talked about it in Chem 11. Okay, so when we went into Chem 11, remember we had the solubility table? And what we would do is we would go, chlorine right here with silver, okay? And what we would do is we would look across and say that's low solubility. But in actuality, it is not. So now what we need to think of is that AgCl, even though it's not soluble, we now have to consider it as AgCl solid is now in equilibrium with Ag plus, AQ, and Cl minus 1, AQ. So what happens is that it exists as equilibrium. Okay, and so this is actually what we're going to be talking about here in Chem 12. Now, some of you may say, well, I don't get it. So what I'm going to do is I'm going to share a screen. Let me see here. Share. And we're going to show you what I mean by equilibrium. So let's say, remember we had something like this in our class, but in this case, what I'm going to do is I'm going to dissolve a piece of silver chloride. Okay, now for silver chloride in chemistry 11, we said that it was not soluble. But if we were to take a look, ooh, this is a little bit more exciting. It has even a targeting scope, molecular scope. What happens is if we take a look at what's happening molecularly, we see that we have silver and chlorine. we break it apart, just like what we had learned before about ionic solids. But what happens in this case, notice not all of the solid breaks apart into ions. And what happens is you get some of these ions coming together to form a solid. And so as a result, what happens in a saturated solution is the ions forming a solid is in equilibrium with the solid breaking apart into ions. And this is what we call a saturated solution or a solution in equilibrium. And the reason why we say nothing more dissolves is because the rate at which the ions form a solid is equal to the rate in which the solids dissolve into ions. And so that's why in a saturated solution, nothing changes. And remember, a characteristic of equilibrium is the macroscopic properties or the visible properties stay constant. So in this case, nothing looks like it's dissolving. And the reason being is it is in equilibrium. Now, one thing I wanted to emphasize in terms of equilibrium is when we went back to your reading. So when you folks read in your textbook, okay, if you take a look on page number 75, what you have on the bottom here is they talk about how the dissolving, okay, is going from a solid to ions, and where you have the ions coming together to form a solid. This is called crystallization. And with a solid going into ions, it's called dissolving. So when we have the equilibrium, what you have is the rate at which it breaks apart into ions or dissolving is equal to the rate in which the ions form a solid called crystallization or solidification. Now, since this exists as a solid, we have to take a look at the equilibrium constant. So if we were to draw this out, write this out, we would have KQ is equal to concentration of Ag plus, concentration of Cl minus 1, all over concentration of AgCl, solid. Now, you remember back in equilibrium, solids are not included. So here it is not included. Okay, remember solids are not included in a KQ expression. So what we can do is rewrite this as KQ is equal to concentration of Ag plus, concentration of Cl minus 1, all over 1. And because we are dealing specifically with ions in solution, forming a saturated solution, we can give it a special K value, and we will call this the KSP, which is concentration of Ag plus, concentration of Cl minus 1. And this KSP, this is called the solubility ion product constant. Or in some books, they just call it the solubility product constant. So basically, what the KSP is the ions in a saturated solution multiplied together. Now, why do we call it solubility ion? Is because remember in the definition, back in the first section, solubility is the amount to form a saturated solution or amount needed for a solution to reach equilibrium. So when we multiply those values together, we call it the solubility ion product constant. Now, one thing I would like you to be aware of is this. The definition of solubility is not the same as the definition of KSP. Okay, that's the one thing you should be aware of. They are related, but they are not the same. Solubility is how much dissolves to form a saturated solution, and KSP is the concentration of the ions in the saturated solution multiplied together. Okay, now what I want to do is I want to give you a couple of examples of how we play around with this particular KSP value. Okay, so for first thing, it says example one, write the KSP expression for AGS. Now, the first thing you need to recognize is this. Here, this is an insoluble solid. Okay, how do you know it's an insoluble solid? Is because if we take a look at this solubility table chart, what happens is we can see that you have S and all others. If we take a look across, it is low solubility. That's one hint. The other hint is, notice they ask you for the KSP expression. When you are asked for the KSP expression, you assume also that it's insoluble solid. Okay, so both ways are for you to check to see whether or not it is soluble or insoluble. One is by using the table, the other is by looking at the actual word, KSP expression. So KSP is an insoluble solid forming an equilibrium or saturated solution. So in this case, once you figure that out, you can go, Ag2S is in equilibrium with 2Ag plus and S minus 2. Okay, this is from the dissociation that you learned previously. So you go, okay, KSP would be the concentration of Ag plus squared concentration of S minus 2. Now, again, since we're talking about equilibrium rules apply. What you have is the 2 of the coefficient becomes 2 in the exponent for the KSP expression. Okay, this is what you had learned back when we talked about equilibrium. Okay, now let me give you another example. So in this particular case, it says here, calculate the solubility product constant, or KSP, of bismuth, which has the solubility of 1.0 times 10 to the negative 7 moles per liter. Now, one thing for you to be aware of, notice I'm asking for the solubility product constant, or KSP, given the solubility of 1.0 times 10 to the negative 7. In this particular case, this solubility is how much dissolved to form equilibrium. Or saturated solution. Okay. Now, so in this particular question, I asked you to make sure you know the difference between solubility product constant and given the solubility. Okay. Again, here, the solubility is how much is dissolved to form equilibrium, while here, the solubility product constant is the ions multiplied together. So what I'm going to do is I'm going to take what we had learned up here about the dissociation equation, and then we're going to solve it. Now, because I'm asking for KSP, I know that the solution is in equilibrium. So what I have here is I'll write the equation. Bismuth 2s3 is in equilibrium with 2Bi plus 3 and 3s minus 2. Now, since we're doing calculations, we have to set up, oh, you know what I'm going to set up if we're doing equilibrium. Okay, got it. Okay, so what we're going to do is we have to set up our ice tables. Gotta love ice tables. Okay, now, so in this particular case, what we have is we're going to start off as 0 because originally there are no ions that are in solution. So what do we do with this 1.0 times 10 to the negative 7? That is the change. So in this case, this is 1.0 times 10 to the negative 7. This would be 2.0 times 10 to the negative 7. This would be 3.0 times 10 to the negative 7. Okay, now again, what happens in this particular case, you have to follow mole ratios. And so as a result, in this particular case, this would be 2.0 times 10 to negative 7. This would be 3.0 times 10 to negative 7. Now, notice I didn't fill anything in for the bismuth is because it's a solid. So we don't need to worry about the concentration. Now, this should look familiar because when we were doing equilibrium, that's KQ calculations, remember we were doing the ice tables, okay? And we went through that in the previous video. So in this particular case, I have my ice tables here. And all I need to do now is, since I have my equilibrium concentration, I just need to plug it in. So I go KSP is equal to the concentration of bismuth plus 3 squared, sulfur minus 2 to the power of 3. So this would be 2.0 times 10 to negative 7 all squared times 3.0 times 10 to negative 7 all cubed. And if I were to do that, it looks like a very small number. So 2.0 negative 7 squared times 3.0 e to negative 7 to the power of 3. And so I get basically a 1.08 times 10 to negative 33. Okay, now that's basically it in terms of setting up the ice table and then doing your calculations. All right, now, what if we were to do it the other way? It says calculate KSP value for copper 2 iodate is 1.4 times 10 to the negative 7. Calculate the solubility in grams per liter. Now, notice here it says the KSP value for copper 2 iodate is this value here. Again, the 1.4 times 10 to the negative 7 in this case is what is the value when you have the ions multiplied together? So how do you approach this is basically exactly the same. So we have Cu IO3 2 is in equilibrium with Cu plus 2 and 2 IO3 minus 1. Again, what we do is we can set up the ice table. Okay, so here we set up the ice table. And here we start off with 0. Now, in this particular case, you remember from equilibrium, this side must go down, this side must go up. Products must go up because you can't start off at 0. So in this case, we can cancel this out. You have x, x, and then you have 2x using mole ratio. So then this would be x, this would be 2x. Now, what happens is, again, you can go KSP is equal to the concentration of Cu plus 2, concentration of IO3 minus 1 squared. So this would be 1.0 times 10 to the negative 7. Okay. And this would be equal to x, 2x all squared. And when you solve for this, you would have 4x cubed is equal to 1.0 times 10 to the negative 7. So x, you solve for this, 1e negative 7 divided by 4, and then raised to the power of 1 divided by 3, cube root. So you get an answer of 0.00292 moles per liter. Now, they want the answer in grams per liter. So you just take, in this particular case, 0.00292 moles per liter times the molar mass of copper 2 iodate. I think copper 2 iodate is 1.9 times 2 and 63.5. So I believe it's 413 grams per mole. And that would give me an answer times 0.00292. And so that would give me an answer of 1.21 grams per liter. Okay. Now, when you take a look, you might say, well, Mr. Chan, why did you use the entire mass of copper 2 iodate? Okay. So in this case, I was looking at copper 2 iodate, the entire mass I used because that was the amount that was dissolved to form a saturated solution. And that's what the word solubility meant in grams per liter. Okay, so that is something for you folks to be aware of. Now, hopefully you see the similarity between this setup and this setup here. Okay, now maybe you can take some time to sort of see, wait, how did this set up? What was going on with the mole ratios? So notice the similarities between example 2 and example number 3, but the only difference is in terms of here you have X, here you have actual values. Now, if you take a look at the example in the book, so let me see here, okay. If you take a look at the sample calculations, you might notice on page 94, they would say, you notice they don't put any ice tables in there, okay? Now, for me, I like to use ice tables in my calculations because then you can see how it is linked to the equilibrium that you learned in the previous unit. Setting up the ice tables, where did I get it? Why did it follow the mole ratios? Okay, versus what they have here in your Hebden text. Nothing wrong with it, okay? But sometimes some people might find it a wee bit more confusing, especially if you take a look at the examples. Hey, when do you use X? When do you put the values in? When on your test or when you're doing your homework, I don't care which one, I don't care which one you use, so long as you know where the numbers are coming from, okay? But honestly, I would start off with making sure to try out using the ice tables and figuring how things work. Now, the last thing I wanted to emphasize was on page number 92. Notice on the top of page number 92, they talk about the difference between solubility, molar solubility, or solubility product constant. And notice it even highlights saying that solubility and solubility product constant are different concepts. So don't get them confused. All right. Hopefully this was a pretty clear lesson. And again, what you can do is work on some of the questions that I'm giving you. And hopefully, with practice, you are able to distinguish and sort of know how to separate or figure out questions like example 3 and example number 2. All right. Thank you very much. Have a great day. Bye-bye.